Today, we are pulling back the curtain on a machine that's so common we barely even notice it, but it's so critical that our world would literally stop without it. This is the secret life of motors.
So let me just ask you something. If you had to pick one single machine that powers our entire civilization, I'm talking everything from tiny pumps to massive factories, what would you say it is? It's not the computer, not the car engine. You got it, it's the electric motor. These things are absolutely everywhere, just silently turning electricity into motion. But here's the really interesting part. Making them run smoothly and efficiently, well, that's an incredible engineering puzzle. It's full of invisible forces and really complex problems. All right, let's dive right into the heart of the machine and see how this all works.
To really get a grip on this challenge, we first need to meet the main players. And in the industrial world, that means getting to know the two titans of AC motors.
Okay, so on one side, you've got the induction motor. Just think of this one as the reliable, rugged workhorse. Its rotor, that's the spinning part, is always kind of playing catch-up, turning just a little bit slower than the magnetic field around it. Then on the other side, we have the synchronous motor. This one is all about precision. Its rotor locks right into the magnetic field and spins at the exact same speed. No slip, no delay. But that level of precision comes at a price. It needs its own separate DC power supply just for the rotor.
And what's so cool is how even within these synchronous motors, the design is totally tailored to the job. You've got the salient pole rotor, with its huge diameter and poles that stick out. It's built for the slow, super powerful rotation you'd see in a hydropower turbine. Then you have the complete opposite, the cylindrical rotor. It's long, it's sleek, and it's designed for the high-speed world of steam turbines and power plants, where it has to run incredibly smoothly.
But you know, these powerful machines, they are not perfect. They have these built-in flaws, kind of like little gremlins in the works that engineers have spent decades trying to squash. So let's take a look at what happens when these motors start to misbehave.
So first up is this thing called cogging torque. Have you ever turned a small electric motor by hand and you feel it kind of click or bump into place? Yeah, that's cogging. It's just a natural magnetic pull between the magnets on the rotor and the steel teeth on the stator. Now, at high speeds, it's not a big deal at all, but when you're trying to run slow, it causes this really jerky, rough operation.
The second big headache, and this is especially true for our precision synchronous motors, is something called hunting. The best way to picture it is like a spinning top that suddenly starts to wobble. That's basically what's happening to the motor's rotor. When the load on it changes out of nowhere, the rotor doesn't just smoothly settle into a new position. Nope. It overshoots, then swings back, and just oscillates around where it's supposed to be.
Let's just walk through that chain reaction. A sudden load hits the motor. For just a split second, the rotor slows down, falling out of that perfect sync. Now, this little bit of lag actually increases the motor's pulling power to try and compensate. But, and here's the kicker, because of its own inertia, the rotor doesn't just catch up, it flies right past the sweet spot. Then it tries to correct again, swings back, overshoots again, and suddenly you're stuck in this unstable wobble. So the crazy part is, the motor's own attempt to fix itself is actually what's causing the problem.
So how in the world do you fix problems like these? Well, this is where the real engineering genius comes into play. Let's look at some of the incredibly clever ways we've learned to tame this electrical beast.
One of the biggest challenges is just getting a large motor started. If you just flipped a switch, you get this massive surge of current, an inrush, that can seriously stress the motor and the whole electrical grid. So the solution was to develop starters that could gently, ramp up the voltage.
Now, the classic, cheap and cheerful solution was the star-delta starter. It works, sure, but to get to full power, it has to briefly disconnect and then reconnect the motor. And that switchover causes this huge electrical and mechanical jolt. A much smarter, smoother solution is the auto transformer starter. It uses a transformer to ramp up the power in steps, completely eliminating that harsh jerk and giving the equipment a much gentler start. And this number right here, this just says it all. The smoother auto transformer starter can deliver nearly double the starting torque of a star delta. What that means is it can get really heavy loads moving way more effectively, all while being a lot nicer to the machinery.
But even the best mechanical starters have their limits. And as this engineer from an online forum points out, if you want truly smooth operation, you have to go to electronics. This insight is the perfect bridge from those old-school mechanical solutions to the modern digital age of motor control.
And that brings us to the VVF drive. That stands for Variable Voltage Variable Frequency Drive. This thing is basically the brain of a modern motor system. Instead of just cranking up the voltage, it precisely controls both the voltage and the frequency of the electricity feeding the motor.
It's like having an accelerator and a gearbox with infinite gears.
And here's the magic behind it all. The real key is to keep the ratio of voltage to frequency, the V/F ratio, constant. And as you can see from this graph, by doing that, the drive can make the motor produce this high, stable torque across a huge range of speeds. This gives you a level of control that was just impossible with the older methods.
So what about that wobbling problem, Hunting? Well, the solution is just beautifully elegant. Engineers embed these special copper bars called damper windings right into the rotor. Now, when the motor's running stable, they do absolutely nothing. But the second the rotor starts to oscillate, that movement creates a current in the bars. That current creates its own magnetic field that pushes back against the oscillation, effectively damping it and making the motor stable again. It's brilliant.
Okay, for our final topic, we're going to zoom out. We're going from a single motor to a system-wide problem that motors create, and, surprisingly, a problem that they also solve. This is what I like to call the power factor puzzle.
So the problem starts with our good old workhorse, the induction motor. When you get a ton of them running in a factory, they draw a type of power called reactive power. Now, this power is essential for creating their magnetic fields, but it doesn't produce any actual, work. It just clogs up the electrical grid. Think of it like the foam on a beer. It takes up space, but it's not what you really want. It just makes the whole system inefficient.
And the solution? Well, it's one of the absolute weirdest machines in all of electrical engineering, the synchronous condenser. Okay, get this. It is a massive synchronous motor that isn't connected to anything. It does zero mechanical work. Its only job is to spin. So why on earth does this thing exist?
Here is the brilliant part. Remember how a synchronous motor needs its own DC power to get excited? Well, if you overexcite it, basically you give it more DC current than it needs just to spin, it starts acting like a generator. But instead of producing real power, it starts producing the exact kind of reactive power that all those other induction motors are gobbling up.
So you just stick one of these useless motors in a factory or a substation. It just spins, it floats on the grid, and by fine-tuning its excitement level, you can have it supply all the reactive power needed right there on site. This frees up the entire grid, it cuts down on waste, and makes the whole system way more stable and efficient. A motor that does nothing is actually doing everything.
So we've gone from these simple workhorses to precision machines, and finally to these intelligent devices that can stabilize the entire grid. The motor isn't just muscle anymore. With modern electronics, it's really becoming a brain. And as we rely more and more on electricity for everything, you just have to wonder, what problem will this incredible machine solve for us next?